Hi, I'm Chiao Hong, and I'm a senior electrical engineering student studying in ASU, and I specialize in hardware design.
Hi, my name is Blake Haddock. I'm an electrical engineer senior at ASU.
Hi, my name is Gene Kim, and I'm a senior electrical engineering student at Arizona State University.
Hi, I'm Karthik. I'm an electrical engineer and I am specializing in digital design.
My name is Roberto Huerta, and I am an electrical engineer specializing in circuit design. I'm currently working as an intern at Intel. Here is a summary that outlines our video progress report. How does our project relate to the public? Who do we hope to help? What will success look like? What are some of the technical
Hi, I'm
difficulties?
Chiao
And the
Hong,
conclusion.
and I'm a
Our project focuses on using FPGAs to solve ordinary differential equations in hardware. This matters because FPGAs can compute these equations in real time rather than traditional computers, which compute them step by step. In fields like automotive engineering, this can be crucial. For example, FPGAs help power advanced driver assistance systems, combining sensor data instantly for features like collision avoidance and lane detection. They also improve electrical vehicle powertrain control, allowing for a smoother and more efficient performance. The same technologies used in aerospace, flight control, and radar systems depend on FPGAs for their speed and reliability. By accelerating ODE computation, we're showing how FPGAs can make these next generational systems safer, faster, and smarter.
For people who we hope to help, people such as electrical engineers need these simulations in order to protect their hardware and reduce the costs of those hardwares. For software developers, they need it to create and debug their software. Other people, such as product engineers, need these for their test cases, and aerospace engineers need it to also reduce the cost and to save human lives, since there are many accidents that occur in that field.
There are three critical factors that will determine our project success. First, our ACL code must execute operations in parallel, because parallel architecture is essential for achieving real-time performance. Second, we need a robust verification strategy, because chaotic systems are extremely sensitive to errors. Third, visualization is also a key. Our differential equations must be displayed clearly on either computer monitors or oscilloscopes to prove our system works in real time and also makes our chaotic behavior visible to our audience.
There are a few potential technical difficulties that could arise in this project. One, we must make sure we meet timing. If the calculations don't finish in the right time, you don't have a number and your method fails. We need to avoid divergence by compounding error. We're going to use floating points to avoid that. We need to implement the RK method efficiently in hardware, but it's going to take some trial and error. We need to handle out of bounds error in division by zero, which is going to the process was invalid after one of those. We have to output the results efficiently and quickly, and we have to gracefully handle fatal errors that require like a stop and restart.
In conclusion, our project is simple but greatly impactful. The goal is to produce a hardware implementation that utilizes the linear processing power the FPGA boards have over CPUs to solve ordinary differential equations. Completing this goal will improve the quality of life of so many different people. Thank you.